The S.O.L.I.D principles are more than just buzzwords, they are fundamental design guidelines that transform good code into great, maintainable, and scalable software. Coined by Robert C. Martin, these principles are critical for any developer looking to build robust object-oriented systems. While many articles explain the what, truly grasping S.O.L.I.D often requires seeing the how in action. In this article we'll dive into each principle, illustrating its core purpose with practical C# code examples. You'll see how these guidelines directly impact your code's structure and maintainability. Let's illuminate these principles with code and clear examples. SS is for Single Responsibility Principle, SRP. The rule: a class should have one and only one reason to change. Imagine a report generator class that's responsible for fetching data, formatting it, and then sending it via email. If the data fetching logic changes or the email service updates or the report format needs adjusting, your report generator class needs to change. That's 3 reasons to change, making it a God object in miniature. This tight coupling increases the risk of introducing bugs. A change to the email logic could inadvertently break the report formatting. The goal: to isolate changes and prevent them from impacting unrelated parts of your system. By separating concerns, each class becomes focused, easier to test, and safer to modify. Here's a visual representation of how a single overloaded class, like our order processor initially, is broken down into specialized single responsibility components. Press Enter or click to view image in full size. O is for Open Close Principle, OCP, the rule. A software entity should be open for extension but closed for modification. Consider a shipping calculator that determines costs based on a standard shipping method. If you introduce express shipping or international shipping, the OCP states you shouldn't modify the existing shipping calculator's internal logic. Instead, you should extend it with new strategies. Modifying existing tested code is risky and can introduce regressions. The OCP promotes adding new functionality by creating new code, rather than altering stable code. The goal: to allow new features to be added without altering existing stable code. This protects your system from unintended side effects and reduces the risk of bugs when extending functionality. This image illustrates how a central component, like our shipping calculator, can be extended with new functionality without being modified itself. Press Enter or click to view image in full size. L is for Liskov Substitution Principle, LSP, the rule: subtypes must be substitutable for their base types without altering the correctness of the program. Consider a base class bird with a fly method. A sparrow, a subtype, can fly, so it's a valid substitute. But what if you have a penguin, another subtype? A penguin cannot fly. If you try to substitute a penguin for a bird in a context that expects it to fly, your program will break or behave unexpectedly. The LSP ensures that if S is a subtype of T, then objects of type T in a program may be replaced with objects of type S without altering the desirable properties of that program. In simpler terms, a child class should never surprise you with its behavior compared to its parent. The goal: to ensure consistency and predictability in your inheritance hierarchies. It prevents fragile base class problems, where a child class's behavior breaks the assumptions made about its parent. This image illustrates how a subtype, like a square, must behave consistently when substituted for its base type, like a rectangle. Press Enter or click to view image in full size. I is for Interface Segregation Principle, ISP, the rule. Clients should not be forced to depend on methods that they do not use. Imagine a single, large interface called iWorker with methods like work, eat, sleep, manage projects, and write code. If you have a junior developer class, it might implement work, eat, and sleep, but not manage projects. This forces the junior developer to depend on a method it doesn't use, potentially leading to empty implementations or not implemented exceptions. The ISP advocates for breaking large monolithic interfaces into smaller, more specific ones. This ensures that a class only implements the contracts it genuinely needs, leading to cleaner code and fewer unnecessary dependencies. The goal? To reduce fat interfaces and ensure that client classes are only aware of the methods relevant to their specific role. This leads to more cohesive and maintainable code. This image shows how a large, all-encompassing interface forces classes to implement methods they don't use, violation, versus smaller, specialized interfaces that allow classes to pick only what they need, adherence. Press Enter or click to view image in full size. D is for Dependency Inversion Principle, DIP, the rule. High-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. This principle is fundamentally about decoupling. Think of a car, high-level module, and its engine, low-level module. Without DIP, the car directly depends on a specific combustion engine. If you want to use an electric engine, you have to modify the car class. DIP introduces an iEngine abstraction. Now the car depends on iEngine and both combustion engine and electric engine. The details depend on iEngine, the abstraction. The car can run with any iEngine implementation, making it incredibly flexible. The goal? To reduce tight coupling between modules, making your system more flexible, testable, and easier to maintain. It promotes a design where components can be easily swapped without affecting the higher-level logic. This image illustrates a high-level module, the car, directly relying on a specific implementation, a combustion engine, which is a rigid connection. On the right, it shows how introducing an abstraction, an engine interface, allows the high-level module to depend on the interface, making it flexible enough to work with any engine type, combustion or electric.